In lesson 7.5, we're going to be talking about pH. To summarize what we already know about acids and bases, we've talked about one definition of acids and bases, and that was the Bronsted-Lowry definition. And according to the Bronsted-Lowry definition, an acid is anything that gives away a hydrogen ion, and a base is anything that accepts that hydrogen ion. So, for example, in this reaction between ammonia and water, the water is giving a hydrogen atom to ammonia. And not just an atom, an ion, because the electrons, both electrons in that bond, stay behind. Okay, and so the hydrogen ion, the H+, is transferred to the ammonia. That means water is acting as an acid in this reaction, and ammonia is acting as a base. And so in the Bronsted-Lowry definition, the focus was on hydrogen ions, H+. But we're going to add another ion here into the mix when we talk about acids and bases in the scheme of pH, and that we're going to start talking about hydroxide as well. So your objectives for this lesson are to relate the pH of a solution to its hydronium ion concentration to determine whether a solution is acidic or alkaline, compute pH, pOH, hydrogen concentration, and hydroxide concentration, and perform one-to-one titration calculations using MAVA equals MBVB, and interpret titration curves for strong acids and strong bases. So let's look at what all this means. In any sample of water, no sample of water is just pure H2O. In fact, in water, no matter how pure that sample is, there's always going to be a certain amount of hydronium and hydroxide. Okay, so what are those ions? So hydronium is formed when a hydrogen ion is given to a water molecule. Instead of H2O, we have H3O plus. Okay? And so in water, what we see is that two water molecules will actually react. Two H2Os will react with each other, and one hydrogen will transfer onto the other one. That makes one ion into hydronium, polyatomic ion, and the other one becomes hydroxide, also a polyatomic ion with a negative charge. And so there's always some hydronium and some hydroxide in any sample of water because this reaction will always happen reversibly. And so that means that those the hydronium and hydroxide can react with each other to form water molecules again. And so in water, it's the balance between hydronium and hydroxide that we're looking at when we look at pH. So if we look at the pH scale, we describe low pHs as being very acidic and high pHs as being very basic or alkaline. Okay, alkaline is another word for basic. And so the scale runs from 0 all the way to 14, with the neutral pH being 7. Okay? And so anything with a pH lower than 7 is an acid, and anything above 7 is a base. But what does that mean? Well, if we look at what's really going on in those solutions, the more acidic a solution is, or the lower its pH value, the more concentrated its hydrogen or hydronium is going to be. So the more hydronium there is in a solution, the lower the pH is going to be. And similarly, the higher the pH, the more hydroxide there's going to be. And since those two compounds react with each other to form water, the more hydroxide you have, the less hydronium you're going to have, or hydrogen ions. They're both expressed the same way. And the more hydrogen ions or hydronium you have, the less hydroxide you're going to have. And at a pH of 7, a neutral pH, we see that we have a balance between those two compounds. All right, so neutral means that you have the same amount of hydronium as you do hydroxide. Now, if you look carefully at this scale, you'll notice that this is a logarithmic scale, which basically means that a difference of 1 pH, so going from a pH of, let's say, 6 to a pH of 5, the pH of 5 is going to be 10 times more concentrated than a pH of 6. And a pH of 4 is going to be 100 times more concentrated than a pH of 6. And a pH of 3 is going to be 1,000 times more concentrated than a pH of 6. So every number that you move along the pH scale, you're multiplying that concentration by 10. Okay? So let's look at some examples of how to calculate the pH. All right, and since pH is a logarithmic scale, we can use the equation to calculate the pH is that pH is equal to the negative log of the hydronium concentration. Now, notice these brackets here are shorthand just for concentration. They refer to the molarity of the solution. Okay? And sometimes, again, you'll see this written as hydronium or just H+. They're both indicating the same sort of thing. Okay? And so, for example, if we look at a 0.1 molar hydrochloric acid solution, we can calculate the pH by saying that the pH is equal to the negative log of 0.1. And all you have to do is plug in 0.1 and hit log on your calculator, and it'll give you a value of -1. And that negative just means that we flip the sign to +1, and we wind up with a pH of 1. So a 0.1 molar hydrochloric acid solution is going to have a pH of 1. Now, what if we want to go the opposite direction? What if we want to know the concentration of a solution with a certain pH? Well, the concentration of hydronium, or hydrogen ions, in a solution is equal to 10 to the minus pH. Okay? So, for example, if we look at a solution with a pH of 9, that means that the hydronium concentration will be 10 to the negative pH, which is 10 to the negative 9th molar. And since this is already good scientific notation, we can leave it just like that. And so you can hopefully see that the higher your pH is, the smaller your hydronium concentration is going to be. Because as this number, this pH increases, this number will get larger. And if you remember in scientific notation, since there's a negative sign here, the larger this number is, the more decimal places to the left we slide when we convert that into standard or long form notation. So just like pH, there's another scale that we don't as often talk about when it comes to measuring the acidity or alkalinity of solutions, and that's the pOH. And the pOH is measured exactly the same way as pH. The only difference is that pOH focuses on hydroxide, whereas pH focuses on the hydronium. And if you look at this scale, you can notice there's a little bit of an exchange between these two numbers. So for example, a solution with a pH of 0 is going to have a pOH of 14. Or something with a pH of 11 is going to have a pOH of 3. Or something with a pH of 7 is going to have a pOH of 7. In fact, the pH and the pOH always have to add up to equal 14. Okay? And so we can calculate the pOH with the same equations that we use to calculate pH, except in this case we're calculating pOH with the negative log of the hydroxide concentration, or we're calculating the concentration of hydroxide with 10 to the minus pOH. Okay? And so the pH and the pOH have to add up to 14 in every single time. Okay? Or another way of thinking about that, if we rearrange that equation based on our other equations that we have, we could say that the hydronium concentration times the hydroxide concentration always has to equal 10 to the minus 14th. This is what we call an equilibrium constant, and we'll get into that in the next lesson. But the idea here is that if you increase the amount of hydronium in a solution, you will decrease the amount of hydroxide by proportionately the same amount. And vice versa. If you add more hydroxide to a solution, you will decrease the hydronium concentration, so that those two will always multiply together to get 10 to the minus 14th. And so we call this the Arrhenius definition of acids and bases, named after Svante Arrhenius. And the idea here is that an acid is anything that can increase the concentration of hydronium of a solution, decreasing the pH and making it more acidic, or base is anything that increases the amount of hydroxide in a solution, which will increase the pH, decrease the pOH, and give us a more alkaline or basic solution. So we can scale this all together and combine our equations into this one helpful diagram. Now it would be a very good idea to pause this video and to write this diagram somewhere on your reference packet where you'll have it when you take this test. Although these equations are in your reference packet, this puts it in kind of a more visual format. Okay, so it shows us how to convert between any of our values. Like let's say we're given the pH and we want to calculate the pOH. Okay, so all we have to do is to go from pH to pOH, we just take 14, which is that number that the two have to add up to, and subtract the pH, and that'll give you your pOH. Or vice versa, if you want to go from pAOH to pH, you just take 14 minus the pOH, and that'll give you your pH. Okay? Or looking at our hydroxide concentration equation and our pOH, In order to go from hydroxide concentration, like let's say you know the concentration of a sodium hydroxide solution, all you have to do is take the negative log of that concentration. That gives you the POH. Or vice versa, you can go from POH, take it 1 times 10 to the minus POH, and that's your hydroxide concentration. Now notice here there's no direct link between hydrogen concentration and POH or pH and hydroxide concentration. When we do calculations where we want to go from the pH to the hydroxide concentration or vice versa, we always have to first either go through hydrogen concentration or the POH. So what if we don't know the concentration of an acid or a base? What if we just know that we have some sort of acidic or alkaline solution, but we don't really know how concentrated that is and don't really know the pH? Well, we can use a digital pH probe to measure the pH or the POH and do the calculations that way, but there's another more traditional way of doing that and a slightly more reliable way, and that's through what's called titration. And the idea is that if we take, let's say we have some sort of acid and we don't know the concentration of that acid, we take a certain amount of it, like let's say 50 or 100 milliliters, and put it inside a flask. And in that flask, we're going to add an indicator. All right, and that indicator, usually we'll use phenolphthalein if we're using strong acids and bases, and the phenolphthalein will change colors as the pH hits 7. All right. And so what that means is that we can add a certain amount of base of a known concentration. We do know the concentration of this base. And we can measure how much base we need to add in order for the acid to become neutral. Because when the acid becomes neutral, when that mixture becomes neutralized, the pH is going to be 7, and you're going to have an equal amount of acid ions and base ions, an equal amount of hydronium and hydroxide. Okay, so looking at this graphically to chart the titration curve of a titration, that's what this process is called, is titration, we can look at the relationship between the amount of base that we add and the pH of that solution. When that indicator changes colors, that tells us that our pH is 7. And that's our equivalence point for a strong acid and a strong base, which indicates that we have the same amount of hydronium as we do hydroxide. So if we know how much base we're adding and we know the concentration of that base, we can then determine what the concentration of that acid is. So to summarize, you should be able to relate the pH of a solution to its hydronium ion concentration, determine whether a solution is acidic or alkaline, compute pH, POH, hydrogen concentration, and hydroxide concentration, and perform one-to-one titration calculations using the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base in a titration, and interpret titration curves for strong acids and strong bases.